All right, good morning. Let me start with some announcements. So first of all, my summer engineering 270 class, I'm planning for that to be in person. That's the current guidance from Clark College. As you probably know, 250 was supposed to be in person also, and I decided that did not feel safe to me, and so I've moved things to be remote. Um, but Clark is wanting people to be back in person as soon as possible, and so 270 is going to be in person, and so that will meet 2 times a week. If you're signing up for my section, um, you should probably be aware that I'm probably not going to record my classes for summer. So it will be an in-person class, and if you don't come to class during the scheduled time, you will not have access to the lecture material. You'll be responsible for getting the notes from somebody else and so on. And so the 6 or 7 people who have been coming to this class regularly and coming in every time, thank you. I appreciate it. And I think it's beneficial for people to be here for the lecture. But summer, probably not going to do this. So we'll be meeting in the STEM building 2 days a week, lecturing there, and that will pretty much be that. There'll be 3 hours of lab during the week, which I'll probably mix with office hours, or maybe throw in an extra office hour a week. But so that's just a heads up. If you're signing up for 270 in the summer, you can factor that into your plans. All right, so my goals for today are to talk about homework 5, which looked good. So I wanted to run through at least the basic setup for some of the questions on homework 5, but I graded question 3 in particular, and it looked good for people who turned it in and showed their work and so on. So I'll go through homework 5. We'll talk about homework 6 if there's any questions. We'll talk about lab 6 if there's any questions. And then I want to get you started on some of the preliminary setup you have to do for lab 7. And beginning this week, we're going to go into the last topic of the course, which is Verilog, something called a hardware definition language. And the homework and the lab for Verilog will involve downloading and installing a software package on your PC, and so that's something that we're going to have to take care of like today or tomorrow, so that you have this tool installed and ready to go as we're lecturing and working on these concepts and so on and so forth. So that's my basic plan for today. Anything anyone wants to talk about, or any questions before we get into all of that? All right. Well, let's take a look at homework 5 then. So I posted grades for this last week, along with some feedback where I thought it would be helpful. And again, try to look at that feedback I post, because it's often specific to the solution you submitted. But let's just run through these. So question 2, I didn't mean this to be as goofy as it was. I inadvertently wired up 2 complemented inputs to an OR gate with an inverted output, an OR gate. So Z1 is always uninteresting. It's always a 0, and D is always a 0. So this is kind of a special oversimplified case of a D flip-flop based machine. And the analysis comes out kind of extremely simple, So I'm not going to go through that one. But let's take a look at machine 3. Well, let's see, that was 2. Same thing happened with machine 1. Had 2 inverted inputs going into an AND gate, so the output of this is 0, so D again is always a 0. So whatever state this machine starts in, it ends up in state 0, and in state 0, Z is equal to 0. So same behavior as here. So let's look at machine 3, which was the question that I graded in detail. And so 2 T flip-flops, and you can choose state names, and I'm going to stick with sort of the kind of canonical state names I use, which would be like S1, S0 to represent T1 is and T0. So Q1, Q0 name. So sort of like that, because we don't have to work too hard to know what the values of our flip-flops are in state S10. The flip-flop values are 1 and 0. We're just standardizing that. And since I always write, you know, Q1, Q0 in that particular order, I don't need to look at this table, right? This is just kind of showing my work, and it's what I'm referring to. But if you do the same thing every time, you don't really need to keep constantly checking back at this table. You'll just know, you know, S01, that's a 01 for Q1, Q0, and so on. So write this table down, but we can largely not worry about it too much. And then write equations for the output of the circuit and for the flip-flop inputs. And you write those in terms of external inputs and Q's and Q bars. So this comes from looking at the circuit and tracing the signals. So let's start with T0. And that comes out of an OR gate. And the 2 inputs are Q0 and Q1. So T0 is just Q0 or Q1. T1 comes out of an OR gate. One input is Q1 bar, and the other input is coming out of an AND gate. And the inputs to the AND gate are this line here, and I'm not going to write down Z because Z is an output, right? The thing that's driving this line, this little T-shaped line here, is Q0 bar. That's the only thing in this set of points that's generating a signal, right? So this is an input. This, we call it an output, but you know, it's presumably an input to something outside of the state machine. This is the thing that's driving the signal. So I'm going to write the name of that, and then that gets ANDed with X. And again, X is an input to the machine, but it's the thing that's driving the input of this AND gate. So when you're writing these equations, you're following back from an input to find the thing that's supplying a voltage to that input. And there should only be one thing supplying a voltage. Everything else is receiving a voltage. So that's Q0 bar ANDed with X. And then Z, the output of the machine, well, that's just coming from Q0 bar. So that's pretty simple of an equation. And now we make our state table. And at this point I can move this out of the way. And so present state, I'm going to write in terms of Q1 and Q0. And I'm going to have an input X. And I've got 8 possibilities. And where you want to draw these horizontal lines is up to you. I tend to have some challenges around keeping things lined up horizontally. So I like putting these lines around groups of 2 rows. All right, so this is basically the input side of the state machine. The current state is a combination of Q1 and Q0, and the behavior of the machine is a function of the current state, right, the present state, and the input X. And so now the next step is just filling in the values of T0, T1, and Z. So let's start with Z. That's the output, and it's just Q0 bar. So this is writing a truth table for an equation. Just take Q0 and toggle it. Toggle as in complement, change ones to zeros, zeros to ones. So that's the output of the machine. And then I need T1 and T0. I'm going to do them in the same order that I did Q1 and Q0. That's really important. If I do Q1, Q0, and then I do T0 and T1, it's not wrong, but it's error prone. It's asking for, a chance to swap 0 and 1. So I'm going to stick to T1 and T0. So T1 is an OR gate. It's Q1 bar or Q0 bar X. Now my recommendation, make a column for Q0 bar. Make a column for Q0 bar and X. Make a column for Q1 bar, and then make a column for the OR of those, so that you're only doing one logic operation at a time. But in the interest of saving paper and time, I'm going to do this kind of in my head as follows. This is the output of an OR gate. I can write down a 1 if this is a 1. I can write down a 1 if that is a 1. So I can evaluate this OR one half at a time. So my first half is just Q1 bar. Well, when is Q1 bar a 1? Whenever Q1 is a 0. So I can by inspection put 1s in these locations. And those are the only rows where Q1 bar is going to be true, because Q1 is a 0. So that's one set of cases where T1 can be 1. The other set is Q0 bar ANDed with X. So if X is a 0, I know the AND is going to be a 0. If X is a 1, then T1 is going to be whatever Q0 bar is. Well, right here, Q0 is a 0, so Q0 bar is a 1. Here, Q0 bar will be a 0, ANDed with 1. This will be a 0. So there's my column for T1. T0 is not nearly as bad. It's just the OR of these two columns. So as long as one of these columns has a 1, T0 will be 1. Up here where both Q1 and Q0 are 0, these will be zeros. Alright, now for the punchline. What is the next state? And so a T flip-flop has this behavior. That if the input to the flip-flop is 0, when the clock ticks, the output does not change. When the input to the T flip-flop is a 1, when the clock ticks, the output toggles. So 0 becomes a 1, 1 becomes a 0. So looking just at Q1, right, so I'm just going to look at this column right here. And based on T1, I'm either going to toggle this if T1's a 1, or I'm going to leave it the same if T1 is a 0. So these top four rows, T1 is a 1, my Q should toggle. So those all become 1s. Here my T is a 0, the output should stay the same. Here's a 1, the output should toggle. There's a pair of zeros, the output should stay the same. And then Q0, I'm going to do exactly the same thing. I'm just going to pick on this column. And if you like and it helps, you can block those off. So there's Q0. And I'm going to use T0 to either leave my input unchanged or to toggle it. Like that. messed that one up. Right, so anywhere there's a 1, which is these last 6 rows, I'm just going to toggle what's in this column. So 0, 0, 1, 1, 0, 0. Up here, the toggle was 0. I'm going to leave the input unchanged. And that's your state transition table. And then the final step is making a state diagram. And so let's make a set of bubbles. And is this a mealy or a Moore machine? The output only depends on the state. If I'm in state 0, 0, the output's 1. Any other state, the output's 0. And you can see that from this equation. If I had an x or an x1 or an x2 or some external input in this equation, then this would be a mealy output. Since it only has these Q's, the values of the flip-flops, the state of the machine, this is a Moore output. It's the only output, so this is a Moore machine. So what I can do when I write my diagram is I can list the name of the state, and then underneath that I can put the value of my output Z. And on this transition arrow, I'm going to list my only input, which is X. So S00 has a 1, all these other states, Z is equal to 0. And this is just saving me from writing Z equals 1, Z equals 0, right? It gives me a picture that just kind of shows me the behavior of the states and the outputs in response to the inputs without getting bogged down by the input is called X, the output is called Z, and so on. And now we just write down what each of these tell us. State 0, 0 with a 0 input goes to state 2. Or state 1, 0. So with a 0, we come down to state 2. State 0, 0 with an input of 1 also goes to state 2. State 1 with an input of 0 or 1 always goes to state 2. So there's a 0, there's a 1. State 2 goes to either state 3 or back to state 1. If the input X is a 0, state 2 goes to state 3. If the input X is a 1, state 2 goes back to state 1. And then state 3 always goes to state 2, whether the input is a 0 or the input is a 1. And so that's the conclusion of the oh yeah, S10 has an output of 1. Thank you. That's the conclusion of the analysis. So any questions about that? Does anybody want to work through question 4? Does anybody want us to work through question 4 as a class? Okay. So question 4, different looking circuit, JK flip-flops. So 2 flip-flops, total of 4 states. I'm going to use the same state table that we used before. I'm just going to call my states S00, 01, 10, 11 for the values of Q1 and Q0. And so let's start with the equations. So what's a good equation for J0? Let's see, where should I do this? I'll do this on a separate sheet. All right, what's a good equation for J0? Q0 or Q1. All right, J0 is being driven by the output of this OR gate. One input from here, one input from here. All right, K0, that just comes from X, right? This is not an output, this is an input to a gate, so there's no signal being driven on this line. X0 is the input for K0. J1, what's the equation for that? So J1 is Z0, that is correct. What is Z0 equal to? Good. Q1 bar XORed with X1. Right, so here's the thing driving this line. It's the output of the XOR gate. One input is X1, one input is Q1 bar. So Q1 bar XORed X1. And then finally K1, and that's coming out of an AND gate. And one input is Q0 bar, the other input is X0. So K1 is Q0 bar ANDed with X0. And we have a single output G0, which we noted was the same as J1, so we don't need to write a separate equation for that. We could. Alright, so let's make a state table. And our state table is going to cover all the combinations of present state and inputs. And we've got 4 possible states, and we've got 2 inputs. So how many rows do we expect in our state table? $16 rows, thank you. 4 inputs, this is basically like a 4-input truth table. And so 2 to the 4th are 16 possible rows. So I'm going to start this on a new sheet. There's our equations. So I'm going to begin with present state. Written as Q1, Q0. And then a pair of inputs. Which will be X1, X0. And we've got our usual set of combinations. This is almost guaranteed to be a question on the final exam, by the way. There's always some kind of state machine analysis question, and then some kind of state machine synthesis question. And that's probably a good 30-40% of the final exam grade. So this is good stuff. Alright, so there's the inputs, if you like, to this state table. And we can put the output over here because the output doesn't really get used other than, you know, in the final diagram. It's not something we have to take into account when we're trying to figure out the next state. So I usually put the outputs right over here next to the input and state combinations. So Z0 is an XOR. Q1 bar XORed with X1. So it's the inverse of this row XORed with this row. And again, I would suggest writing a column for Q1 bar and then doing an XOR of that with X1. But I think we can wing this in our heads. But I will wing it in pencil just in case. So Q1 bar, that's the complement of this row, XORed with this row X1. So this is going to be a 1, 0 will be a 1. These will be 1, 1s, which will be zeros. This will be a 1, 0, which will be a 1. These will be 1, 1s, which will be zeros. These will be 0, zeros. And these will be 0, 1s. And then 0, zeros. And then 0, 1s. Alright, now we want to figure out what the next state is. So to find the next state of a JK flip-flop, we use this table. If both J and K are 0, the output does not change. If the inputs are 0, 1, the output resets. 1, 0 sets. 1, 1 toggles. And the whole setup is, if I know what J1 and K1 are, and I know the current value of the flip-flop, that's Q1, I can figure out the next value, Q1 plus, using this kind of table. Alright, so J1 is just going to be equal to Z0, so I can just copy from the Z0 column to the J1 column. So that's J1. K1 is an AND gate, X0 ANDed with Q0 bar. So anytime X0 is a 0, I know K1 is going to be a 0. So I can fill those in right away. And then if X0 is a 1, K1 is going to be whatever Q0 bar is. So up here, Q0 is a 0. Q0 bar will be 1. Here Q0 is a 1. Q0 bar will be a 0. These will be 1s. And these will be zeros. And then J0, K0, these are simpler equations. J0 is just the OR of the two state outputs. So Q1 and Q0 are both zeros. This will be 0. If any of Q1 or Q0 is a 1, these will be 1s. And then K0 is just the value of X0. So K0 is just the same as X0. So this just alternates. And now the last step of the table is to figure out the next state. So let's figure out what the new value of Q1 is based on the current value of Q1 and the J and K inputs to flip-flop 1. And we have, if we like, this handy JK flip-flop function table. So Q1 is a 0, J1 and K1 are 1, 0. What's the new value for Q1? And if you want to just like shout this on a microphone, that's fine. Yeah, so we're seeing a 1 and a 0. That's always going to set the flip-flop output to be a 1. It doesn't matter what the current state of Q is. 1, 0 always gives an output of 1. So this is going to be a 1. Here's another pair of 1 zeros. Those will be 1s. Here's another 1 0. That'll be a 1. Here's a pair of 1 zeros. That'll be a 1. So if you like, you can sort of do these instead of doing 16 of them one at a time. Once you've figured out for one particular combination what the new state will be, you can just go ahead and fill that in. Alright, what about the second row? J and K are 1s, current state is a 0. What should our output do? So J and K are 1, Q1 is a 0. So if J and K are 1, the output should change state, so it should go to Q bar. And since the current value of Q is a 0, the complemented value is going to be a 1. And down here's another case where we have a pair of 1s. But in this case, the current value of the flip-flop is a 1. So when that toggles, this is going to become a 0. Just making sense? This is the most complex type of flip-flop to fill in these tables for, because you have to look at two inputs and you have to look sometimes at the current state to figure out what the new state is. So this third row, J and K are 0, 0. Our function table tells us Q does not change in that case. So if these are both 0, 0, whatever the current value of Q is, that's going to be our new value of Q. Well, so in this third row, current value of Q is 0. That's a 0. These two rows also have J and K at 0, 0. Current value of Q is 0. These will be 0. There's another 0, 0. Current value of Q is 1. This is going to be a 1. And these two rows, 0, 0. Current value of Q is 1. These will be 1s. And then we've got two rows left where J is a 0 and K is a 1. Well, if J is 0 and K is 1, our output is just a 0. And it doesn't matter what the previous value of Q was. 0, 1, output always goes to a 0. So that's a 0, and that's a 0. And there you go. Alright, Q0 plus same thing, right? Same type of analysis. So I'll run through that one more quickly. So J and K are 0, 0. Q0 should not change. So this will be a 0. That's it for 0, 0. 0, 1, the output is going to get reset. So this will be, oh, here's another 0, 0. So output does not change. Alright, 0, 1, the output should get reset. And that's it for 0, 1s. 1, 0, the output should get set. So this will be a 1, this will be a 1, this, and this, and this, and this will all be 1s. And then 1, 1 for J and K, the output should toggle. So all of these remaining rows where J and K are both 1, Q0 should toggle. So here it'll toggle from a 1 to a 0. And here it'll toggle from a 1 to a 0. And here Q0 is a 0, so it'll toggle to a 1. And here Q0 is a 1, so it'll toggle to a 0. Alright, that's your state transition table. And it shows you all of the information you need to draw a diagram. But it's also a form that lets you show exactly how you got all the data that you're going to use to draw your diagram. And so when I grade a state machine analysis problem, typically, I look at the diagram first, see if it looks correct. And if it does, then I'll come back and eyeball this table really quickly, make sure it basically matches. But if your diagram is wrong, if there's an arrow going to the wrong place or an output that's wrong or something, I come to this table immediately and I start looking to see, did you get these right? Did you get these right? And these, and so on, and try to figure out if this was, a simple mistake or a conceptual issue. Because, if I change one of these values, if I accidentally use the equation for J1, or if my equations are wrong to begin with, if I had a complement over a term that shouldn't be, all of this is going to change and your diagram may come out wildly different, right? But that's not a conceptual issue. That's a human error, which is forgivable, easy to do, right? So not a lot of points. So this is a really important part of doing these problems, even though the final product is the state diagram. The table really sort of tells the person looking at the diagram where that diagram came from. So do your most careful work putting this together, and then we can try to draw a diagram. And this will be fairly ugly, I suspect, because of my drawing skills. So Z0, is this a Moore or a Mealy output? Does it depend on only the state or a combination of state and inputs? It's a Mealy output. Good. You can look in the first 4 rows and you can see these are all the same state, 0, 0, but sometimes the output's a 1, sometimes it's a 0. So this is Mealy. And so when I draw my diagram, I'm going to use something like this. I'm going to have a state name. I'm going to have a transition arrow. I'll list my inputs, which I'll do as x1, x0 slash, and then I'll list my output, z0. And putting the output on the arrow lets me have a different output depending on the input combinations. So if I'm in state 0, 0, some of my arrows may say the output is 1, for example, in these 2 cases, or it might say the output is a 0, like in those cases. And if we had a Moore machine, we could still use a state diagram like this. We'd just be listing more information than we needed. Because if in a Moore machine, if this state corresponds to an output of 0, every arrow coming from here would say /0. And if the output was 1, every arrow would say /1. So using a different key for a Moore machine is just a way to simplify the diagram. Right, but in the case of a Mealy, we have to make the output a function of the input, so we put it on the transition arrows. Alright, so let's see what kind of trouble we can get into. Alright, so I'm using my standard state table names, where this would be 0, 0, 0, 1, 1, 0, 1, 1. And so let's start drawing some arrows. So let's just look at state 0, 0 first. So this state right here. And we can move to either state 2 or state 0. So in some cases, we're going to move to state 2. In some cases, we're going to stay in state 0. Alright, so this first case, state 0 to state 2, happens when our inputs are 0, 0. And in that case, our output is a 1. So 0, 0 / 1. This second row is when our inputs are 0, 1. And in that case, our output is also a 1. And then these two cases where 0, 0 goes back to itself are inputs of 1, 0 or 1, 1, and each of those have an output of 0. Alright, we're just going to keep going. Have a great day. Good luck with the buttons. Alright, bye. Alright, state 1, this one doesn't have as nice a pattern, so let's just do these one by one. So state 1 with an input of 0, 0, we go to state 3. So that's a 0, 0, and the output is a 1. State 1 with an input of 0, 1, we go to state 2. So here's 0, 1, and the output is also 1. State 1 with an input of 1, 0, we stay in state 1. And the output is a 0. And state 1 with an input of 1, 1, we go to state 0. And the output is a 0. Alright, state 2 goes to either state 3 or state 1. And so I'm going to start filling these in a little more quickly. So input of a 0, 0, output is a 0, and we end up in state 3. Input of 0, 1, we're going to go to state 1. And our output is a 0. Input of 1, 0 will go to 3. And our output will be 1. And input of 1, 1 will go to state 1. And our output will be 1. And then our last four possibilities, if we're in state 3, we're going to go to either state 3 or state 2. And our outputs will be 0 or 1. So state 3 with a 0, 0 will take us back to state 3 with an output of 0. State 3 with a 0, 1 will take us to state 2. And an output of 0. State 3 with 1, 0 leaves us in state 3. So input of 1, 0, and here we have an output of 1. And then finally state 3 with an input of 1, 1 brings us to state 2 with an output of 1. So there's an input of 1, 1, an output of 1. And there you go, there's your final answer for question 4. So that's a ton of work, right? And really almost no part of it is easy. I guess writing the equations maybe isn't too bad because we've been doing that for a number of weeks. But even that is not without its complications because we have to trace these signals and find the driver. So writing the equations is a little bit involved, and then filling in this table, well, that part's not too bad, this part isn't too bad, and this part takes considerable concentration, right? And then turning this into a diagram, while it's not hard to, you know, draw part of your diagram based on this first row. The problem is you've got to do that 16 times, right? And you've got to try to do it without mistakes. So this is fairly challenging in itself. So these problems are long, right? They take a lot of work. They take a lot of pages to show your work, and they're kind of hard to check, right? Unless you know ahead of time what this machine is supposed to be doing. I can't just look at this and say, yeah, that looks right. I have no idea, right? Now, I don't think I made any mistakes here, but it's possible. And one of the challenges here is unless you're told, you know, this machine is doing such and such, you can't really look at this and say, oh yeah, it makes sense, right? Now you could do an analysis and then do a synthesis question, but that's a lot more work, right? But homework 6, we're going in the reverse direction. We're starting with these and trying to come up with something like this. And if you really wanted to test your understanding, that's one possibility, is try to design a JK based state machine that realizes this diagram. But particularly with JK, you probably won't end up with the same machine. There are multiple machines that will all have this same diagram. So if we go through our synthesis process, the stuff we did last week, the stuff you're doing on homework 6, to come up with a circuit to achieve this, we probably won't actually come up with this circuit, but we might be able to get close. So these are partially an exercise in faith. Yeah, go ahead.
I have a question.
Yeah.
So, looking at the top left, you have 1, 0 over 0.
Mm-hmm.
1, 1 over 0. Could you theoretically combine them and put 1 don't care over 0?
Maybe you could, but I would say don't do that.
Okay.
That's only because it makes it slightly harder to read the diagram. Oh, is that what the tilde was? Was it don't care?
Yeah.
Oh, okay. That makes sense.
Try to simplify it so it's more visibly understandable.
Cool.
At least for me. So.
Yeah. Okay. Cool. No, that's good. So that's a way to clean up the diagram, right? To have less stuff on here, fewer lines. But I think for reading it, it's probably the way that you would typically read this. It's probably most useful to have, you know, the actual explicit inputs for all those combinations. We'll see some examples where that would be ridiculous, right? Where we have, you know, 10 inputs and 9 of them do one thing and 1 of them does another thing. And so in that case, which is a future homework problem coming up, we'll say you're allowed to use wildcards, to use a don't care, or to put multiple inputs and so on. But in general, for something like this, right, if I'm in state 0, 0, and I see the input is 1, 1, it saves the person from thinking like, oh, okay, 1 don't care, that would be my arrow. So, but it's the same information either way. All right. Other questions?
I have a question for Lab 6.
Okay. Let me pull that up. Hold on one sec. Labs. All right, Lab 6.
I am personally struggling with the logic behind the yellow lights. I have the D flip-flops working correctly and all of the other things, The only problem is yellow light is on when the green light is on for
Okay.
a direction.
Okay. So that actually sounds like you got most of it.
Yeah, but I don't know how I can change that without affecting the light logic.
Okay. So so the way we broke this down was to, instead of doing kind of the traditional state machine design or synthesis process that we talked about last week, I suggested looking at your Lab 3 circuit control and think of a part of your Lab 3 like this. You've got 3 car sensors, west, south, and east. And you've got a west green, a south green, and an east green. And you've got, red outputs also. But we're going to think about these green lights, right? And we're going to think about this one lane at a time. So we're really just going to kind of think about a circuit that takes in 3 inputs and says, does west have permission to go or not? And so for one particular lane, right? So one lane, we have this green signal, right? And so this thing right here, this is your old green from Lab 3. So it turns out, for east, green is just equal to east. If there's a car to the east, it's green. For south, it's basically south and not east, and for west, it's not south and not east. So those equations, when you were done with all the simplifications and the final versions in Lab 3, the green lights are relatively simple equations. All right, so whichever lane we're looking at, we do the following. We have green, let me call this old G for old green, and it goes into a delay circuit. And this gives us a delayed old green. And then we made a truth table. And we thought about these 4 situations. So suppose your old green, let's try this a little differently from how we did it before. Let's look at old green and delayed old green. All right, so here's your Lab 3 permission circuit saying don't go. Here's where it changes to say go, and here's where it changes to say don't go. And we have these delayed transitions coming out of your pair of D flip-flops, right? So we've got 4 regions here, right? So what causes old green to change from 0 to 1? What's the event that's happening right at this point that's causing this transition? Like in plain words, what causes a light to go from not green to green? That's when a car either shows up at the intersection. Right. A car is at the intersection and has the highest priority. Either a car with higher priority has left, or you know, this lane has higher priority than any other lanes with cars, and a car just showed up here. So this is someone pulling up to a light, and your circuit is saying, hey, it's your turn to go. You've got permission. And this transition right here is 2 to 4 seconds later. And this transition right here, when your lab 3 green goes from 1 to 0, says car does not get to go. Maybe there's no car there, or maybe a car with higher priority showed up at another lane, and so this car, you know, suddenly does not have a green light. And this is again 2 to 4 seconds later. And so we have 4 regions, right? Here we have a 0, 0, here we have a 1, 0, here we have a 1, 1, here we have a 0, 1, and here we're back to a 0, 0. So let's just think of what these 4 scenarios correspond to in, you know, driving a car around town. 0, 0, well, that's, you know, several seconds after some car that had permission to go is gone, right? Or a car with higher priority showed up. So if there's no car sitting there, or there's a car with higher priority on another lane, and it's been that case for a few seconds, this is a red light. If your light is currently red and then a car shows up at that light and that car should have permission to go, we know from experience the light does not immediately change to red, to green. The light stays red because we're waiting for somebody else who has a green light to go through a yellow light and then get to a red light. So as soon as you show up at the intersection, the light does not change right away. It takes a few seconds, right? Unless you're a fire truck. And so after a few seconds, though, that's when we get to a green light. And then when we either leave the intersection or a car with higher priority shows up on another lane, our light does not immediately go to red. It changes to yellow. And then a few seconds later, it goes back to red. So this kind of thought analysis tells us what our light should be doing based on the old green and the delayed old green. And so we can copy that information into this table and say, you know, if inputs are 0, 0, this should be red. If input is 1, 0, this should be red. If input is 0, 1, this should be yellow. And if our inputs are 1, 1, this should be green. Alright, once we've done that, we can get back to your original question by adding 3 more columns to show the value that we want for green, yellow, and red in each of these 4 situations. So in this first case, we want a red light, green and yellow should be off. In the second case, we want yellow, red, and green should be off. Third case, we want red, yellow, green are off. Fourth case, we want green, yellow, and red are off. And so now you build 3 circuits, each driven by your original Lab 3 green signal and the delayed version coming out of your flip-flops. Those 2 things become inputs to a circuit for driving your true green light, which is just the AND of these. Your yellow light, which is just, you know, this complemented ANDed with that, and your red light, which is just the complement of the delay. And so if you implement this truth table, there's no way that the yellow light and red light, or yellow and green, can be on at the same time. Yellow should only be on in this combination. This is a 0, this is a 1, and in that case, green and red should both be 0. So I don't know if you were working through this design process or if you were trying to do something different. And there are different ways to do this. This was just the way that we talked about in class last week. If you're not doing it like this and you're doing something different and you want to try to get that approach you're working on to do only one light at a time, that's probably a great thing to go over in office hours, so I can actually look at your circuit and you can show me your equations and tell me your logic and so on. If you're doing it in this style, right, if you got this far, then if two lights are coming on at the same time, it's almost certainly a wiring issue. All right, and if you're going to come to office hours, if you want, you're welcome to email me a copy of what you've got written so far for your lab. If you have this stuff written out, or if you just want to, scan it and send it to me in email, I can have that, and then we can talk about that in office hours if it's not in a forum where you can screen share and so on. All right, good. All right. Other questions? And remember, Lab 6, you need to demonstrate your circuit to me, because that's a hard one to do with screenshots. So you'll want to come by office or lab hours and show me your working circuit. So that's that last part. Yeah, video will work fine. So if you want to take a video and post it on YouTube or something, you can post it as unlisted, so it's not public, and send me a link to it. That would be fine. If you try to send me a Google Doc or something, that's unlikely to work, because Google Doc always tells me I don't have permission to see the files that people send, because there's so many layers of Canvas and email and all that stuff. But YouTube links work pretty well. All right, well, let's do a break. Let's come back at 9:08, and we'll start talking about hardware definition languages and software that I want you to download and install, and we'll start in on this last major topic of the course. So I'll see you back here in about 4.5 minutes. Alright, welcome back. Alright, so our last major topic for the course is a programming language called Verilog. And Verilog is not a usual language in the sense of Python or C or Java or something like that. Verilog is what we call a hardware definition language, or an HDL. And it looks like C or Java or other C-based languages, but it's really not. It's a way to describe a digital circuit using a set of statements that look like a computer program. And it's a really powerful concept to be able to write, a set of statements that basically say what we want a circuit to do, and then have some tool that will take that description and basically design a circuit for us to do whatever we're asking. And so Verilog is one such language. There are others, VHDL being the main other one, but it's a different concept, right? We've been spending the past 7 weeks looking at problems we want to implement, a traffic light controller, for example, and thinking about it as a state diagram, and then writing truth tables, and then making equations and simplifying those with K-maps and putting those together, and maybe doing that as part of a larger state machine synthesis where we're trying to come up with combination of flip-flops and combination of logic and so on, and that's important stuff to know, right? That time is not misspent, but it's not what we usually do in practice, right? When we're designing a traffic light controller for a customer, right, we probably are not doing the kinds of things we're doing in Lab 3 or Lab 6 or in Homework 6 and so on. We're probably using software to come up with the actual design, and our job as engineers is to tell the software what we want. And how do we tell a program? Computers are not very, good at understanding English. They're not good at kind of thinking. So how do we tell this relatively, uninspired piece of software what we want this circuit to do? Well, we use a language that the computer can understand. That's a hardware definition language. And so we're going to spend the next couple of weeks playing around with this HDL called Verilog, and looking at how we can describe circuits to these tools, and how to use these tools to come up with truth tables and arrangements of flip-flops and all this other stuff that we've been doing manually. So a few resources to be aware of on the on Canvas. I'm doing my student view, and it's very strange because it's got I haven't done my midterm yet. Okay. A couple of resources to look at on here. So the first one is down under Labs on Lab 7. There's this Introduction to Verilog, and there's an HDL Quick Start Guide, and there's Lab 7. And all three of these pieces go together. And I'll post Homework 7 once Homework 6 gets turned in. But Homework 7 will be different from the other homeworks. It will be like Lab 7. It will be a series of exercises that you do using this software for working with Verilog. So Verilog Intro is just this short document I put together a few years ago that gives you kind of the punchlines of some Verilog. So there's a lot of sample code in here. There's some discussion of different ways to use this language and so on and so forth. And we'll be going through this over the next few classes and working through some of this in detail. The HDL Quick Start Guide is different. This is a step-by-step set of instructions that you follow for basically getting going with this tool, which is called the Aldec Active HDL Student Edition. And this is fairly uninspired, right? This is trying to show you how to use this tool. And a lot of times when you learn to use a new tool, whether it's, you know, this software or Eclipse or, you know, something else, it's like, you know, click here, go to this menu, click here, uncheck this box, click here, say okay, continue. It's not necessarily going to leave you with a lot of you know, higher level knowledge of what this tool is about, but this is the bare bones. This is what you have to do to live and work with this piece of software. And we'll go through this in class together, starting in a few minutes. And the more you do this, the more times you do it, the less you need this document, until eventually it's just second nature, because you've changed and compiled and simulated your code 200 times now, right? And it's like tying your shoes. You don't need the picture on the wall anymore. It's automatic, right? And we're going to do this so many times that all of this will become second nature. But when we're getting to that point, right, you may find yourself going through this quick start guide step by step. It's 3 pages, so it's not all that quick, but it's you know, just the things that you absolutely need to do to get the software to work for you. All right, so all of this is prefaced by downloading and installing this thing called Aldec HDL. And so this is the thing I'm going to ask you to do, if possible, today. Or possibly tomorrow. But ideally, you've got this on your machine up and running by the next class on Wednesday, so that you can play along while we're doing things in lecture, and you can also, you know, start doing some of the things that we do in lecture on your own, and getting a feel for the software, and most importantly, running into problems, right? You want to run into problems early so that you have time to try to fix them, and if you can't, ask about them in class, and if that's not enough, come to office hours or come to lab hours and screen share and so on and so forth, right? This takes time, right? Now this is a free piece of software. There are versions of software that do the same thing that may cost, you know, $200,000 a year to get a license. And that $200,000 a year software you get is filled with bugs, right? And part of what you're paying for is the phone support or the Zoom support, so that when you run the software and it says, hey, when I type these things, it's supposed to do this, but instead, you know, my CPU burst into flames. And you can talk to a consultant and they'll say, oh, you forgot to click the checkbox that said don't burst into flames, right? So even when you get, you know, the professional quality tools that have been out there for years and are used by, you know, thousands of engineers, you're going to run into bugs. So guaranteed with the free student edition, you're going to run into bugs. And that's part of the process of using these kinds of tools. So you got to leave yourself time for that, which just means start early, right? If you've got a total of 10 hours to spend on this, spend the first few hours sooner rather than later, right? If at all possible. I know there's scheduling issues for all of us, but the sooner you can start on this stuff, the better your experience will be. All right, so download and install the HDL Student Edition from here. So click through that link, and you'll come to this page, and right here at the top, there's a free download Student Edition. So click that. You got to fill in the form, right? They've never spammed me. But they're going to send you a link that lets you download and install the software. So you got to give them a valid email. I don't know how much the rest of this needs to be valid, but I would just go ahead and put it in. great website design here. You can't actually submit it until you take this message and bring it out. And then you can say register. All right. Go ahead and do that. They should send you an email link within like, a few seconds. So I tried this last night, and I got my email link, a few seconds after I said register. And the email looks like this. Oh, of course I deleted it, but let me see. Alright, so the email looked like this. So, bunch of links. This is the only one you care about. Right, so these are for other pieces of the system, but go ahead and click on this link, and it should take you to a download page. Tell them you're not a robot, submit, and it should give you a download option, and then just save that, and then run through the installation, and it's pretty straightforward. Take the defaults if it gives you options, and you're good to go. All right, so one of the downsides of this is this only runs on Windows. So what does this mean? If you've got a Windows machine, it's one of those cases where you're lucky, right? If you're running Linux, this works okay under Wine. It's got some quirks, and you'll see those because the software will crash on me periodically. But using Wine, the Windows emulator, is a pretty good solution for this. If you're running OS X, I don't know how you run Windows programs on OS X. I've been told in the past by some students that this is possible and that it works reasonably well. I've been told by some students that it doesn't work at all. So you may need to, if you don't have access to a PC, you may need to get into campus and get a PC there. But if this is a problem, if you don't have a Windows PC, if you don't have a way to run Windows software on whatever machine you have to do, you gotta let me know. All right. So if this is a problem, let me know this week. All right, and I will do what I can to help you. There are other versions of different software that you can use instead of the Aldec HDL software. There's a version that I actually think is superior to this in a lot of ways, that runs perfectly well on Linux, and it should run on OS X and so on. But you got to take care of that like this week, right? So if the day the lab is due, you come to me and you say, I can't run this software because I have a Mac, there's not going to be a lot of sympathy there, right? Because we can't really do a whole lot in one day. It's an entirely different system you would have to learn, different tool chain, and so on and so forth. But if you let me know that, right away, like today or tomorrow, we can work through that and I can get you going on a different system. And the other thing is, in industry, if you're doing this as part of your job, these tools change all the time, right? The tool that everybody wants to use today is not the same tool everybody will be using next month or next year. And each time that the tool is re-released, it changes. And I spent about 3 or 4 hours last night trying to learn how to use the current version of this tool because they changed a bunch of stuff. Right, and I haven't used it in a year since last spring when I taught this course before. So whatever frustration or aggravation you feel trying to learn this tool or possibly having to switch over to another tool is kind of good practice, right? Because this is sort of the nature of the beast. Companies live and die by how many times they force you to rebuy their software, right? And so companies always come up with new versions and changes and incompatibilities with what you used to do to compel you to, get a new version of Office or this software or that software. And so if we're in this business of engineering and computers, you're going to be constantly relearning tools and encountering bugs and finding workarounds. So don't take those things as setbacks or bumps in the road. Take them as part of what you're learning to deal with and get good with. And you already know this if you've done anything on computers. There's always these kinds of issues. So that's my pep talk / splash of cold water on using this software. With that said, this software is fun to use, right? Once you've got it working and you've got the sort of development process down to a habit, it's pretty fun because it lets you very quickly design fairly complex circuits and then simulate them and actually generate timing diagrams that show you what your circuit is doing as you change inputs and so on and so forth. So I can do some of this from my Linux system, right, using this emulator called Wine, which is an acronym for Wine is not an emulator, but it's actually a Windows emulator. So I can do some of this on Linux, which means I can, do my usual screen share setup that I've been doing all quarter. But some of the more advanced stuff I'm going to have to do on a Windows laptop, which means I'm going to be taking my document camera and pointing it at the screen of a monitor, and that's going to be a little goofy. So this will get a little wonky at times, which is why it will be super helpful if you have the software yourself running when we're going through things in class, so that you can be seeing what should be happening on your system instead of trying to read it from a fuzzy screenshot of a monitor. All right, so go ahead and download the Aldec software, install it, and let's see how far I can get with this. So this is the main file that got downloaded for me yesterday. Active HDL SE 2022 x64 main setup.exe. And when you run it, it's the usual experience. So splash screen, something weird just happened. Splash screen, and just click through all the options. Something just went haywire. All right, let's try it again. So what's happening is this is bringing up the install dialog on a different monitor, and it's being a little wonky trying to move that. Alright, it's not going to cooperate. But anyway, click through the options, follow the regular setup, accept the license terms, and it will ultimately leave you with a file in your C drive called Aldec, a directory called Aldec, and for me, it put my stuff under here. There's a bin directory, and under there's an executable called AVHDL. And if you check the right boxes on your system, it'll let you install a desktop icon, and so you'll just get a little clickable box for avhdl.exe. and it'll show up in your start menu presumably and stuff like that. So let me just run this from my point and click. So avhdl.exe. Let's see how this does. Like I say, I spent a few hours with this last night, but I did not play with it on a double desktop, double monitor setup with Zoom running. So I understand I may use Active HDL only for educational purposes. Any other use requires a commercial license. So we're fine with that because we're in school here. So I'll say OK. And here's the window that comes up. All right. So your homework, if you like, for today or tomorrow is to get this far, right? Go to the website, ask for the student edition, get the email, click on the download link, download it, install it, follow the steps, get to the point where you can start Active HDL and get to this screen. All right, we've only got 20 minutes left. So there's a few ways we can go here. I can start talking about Verilog, or I can run through a quick demo of this software to kind of show you where we're heading. And I think I'm going to do the latter first. I'm going to show you a really quick start to finish design example using this tool, just to give you an idea of what it is we're working towards. And then Wednesday we'll start talking about Verilog, the language, in detail. And then next Monday, I believe, is a holiday. I think that's Memorial Day, so we missed that class. And then next Wednesday we'll have class, and then that's pretty much it. Then we're down to week 10. So let's do a quick run through of a design process here. We'll see if it works. No guarantees, but let's try this. So let me do a fresh start here. Alright, I'm having a hard time. I also did not try this with my CPU overloaded the way it typically is. My other option is to lecture from my Windows laptop, but that would also mean no recording, and I don't want to pull the recordings out from people at this point in the course. But that's what got me going on thinking about recording for 270, by the way. Alright, let's try this one more time. If this does not work, then I will talk about Verilog instead, and I'll get my second monitor, my third monitor set up for Wednesday. But let's try this once more. Last try. Okay, I'm having a problem with monitor size, I think. Alright, I'm going to skip this for now because this is working on my main monitor. And when I put it on the smaller one, it's kind of freaking out trying to redraw the window and doing that kind of stuff. So Wine, by the way, is a decent tool. It's been around forever. It's a tool that runs under Linux and will, to some degree of success, run Windows executables. Some things it works very well on. Some things, in particular games, it works very poorly on. Aldec, it's worked for me in the past, and it was working yesterday, but it apparently is not working well when I have two monitors set up with different resolutions. So I will have to go to plan B Wednesday, which is to actually run this on a Windows machine and just put a camera in front of the display and let you see it from there. And I don't want to try to do that right now because just wiring up the monitor is going to take more time than we have. So I will switch gears right now. And let's talk about Verilog. So you've got this quick intro that you can click through on Canvas. But here's some of the main ideas. Suppose you want to design, I don't know, a traffic light controller, for example. So let's think of a Lab 3 traffic light control. And we've got 3 inputs. And let's do a simplified version with just 3 outputs for green west, green south, and green east. And I don't have to draw this because you probably see this when you close your eyes. But here's our intersection. And east has the highest priority. And so our equations might be something like green east is just equal to east. Basically, if there's a car here, east is green. If there's no car on the east, but there's a car on the south, then we want green south to be asserted. So it's just southeast bar. And green west is no car to the south, no car to the east. So those are the most simplified equations for the green light part of Lab 3. And then red east, it's just the complement of the green. So we can, sketch a circuit with AND gates and inverters to produce these signals. We can go to a proto board. We can get a 7408 for an AND, a 7404 for an inverter, and we can connect wires together to mimic the circuit design that we draw on paper and come up with a circuit that, you feed these 3 inputs in, east, south, west, and it generates these 6 signals. That's the business we've been doing so far. So good question. Would you have to include W for green west? So the way I'm doing this, if there's no cars present, west gets a green light. And it just makes my equations a little simpler. So there's no cars, west is green. Car only on west, west is green. So it's got 2 cases. But yeah, if you wanted everything to be red, if there were no cars, then I would also put west in here. And then it would have the same pattern. So here's the idea. The process of going from, this to an actual proto board with chips on it is kind of mechanical, right? Once you know all the steps, you kind of do the same thing, and if two people follow the exact same steps, they may end up with exactly the same proto board layout. Now, where you put the chips in the proto board, how you run the wires, and so on, that's going to be different from person to person. But we could describe a very detailed step-by-step procedure for, placing components in a proto board, running wires, what color to use for what wires, and so on and so forth. And we could completely automate this process. And this is sort of what these hardware definition languages do for us. They let us describe our circuit in terms of the behavior we want. And this is really useful when you're designing a circuit with 1 million gates in it, right? So this traffic light controller, we would probably have one 7408, and we'd use 2 of the AND gates here. And then we'd use one 7404, and we'd have, 2 inverters. And so, 3, 4 gates, 5 gates, south bar, right? So imagine extending that to a circuit that has 1 million gates, right? So hundreds of thousands of equations, and throw on top of that flip-flops, and your state diagram that has, 1,000 different states in it, and so on. And trying to do that by hand is really not feasible, right? It's incredibly complex, and even if you were able to do all of that, trying to build that with a proto board or a circuit board or something, it's not going to happen. And so just like, writing assembly language code, if you've done any assembly language, trying to write assembly language code for something that adds 2 numbers, fairly grueling, right? Trying to write assembly language code for something like a web browser or an interactive 3D immersive game, right? It's not going to happen. So in software, we've come up with other languages that will translate things into assembly language. That's kind of the ones and zeros of a software program. Well, on the hardware side, we've come up with languages such as Verilog that let us take a high-level description of what we want a circuit to do and changes it into these things, and truth tables, and ones and zeros, and K-maps, and all of this stuff. All right, so Verilog and VHDL are the two main languages that people use. Verilog seems to be a little more popular. It has, to me, fewer quirks than VHDL. VHDL was designed by committee. It was actually designed by the government, I think. And it's got some things that just feel kind of odd to people, including me. And so Verilog is a little more common in industry, but the concepts are going to be the same, whether you're using Verilog or VHDL. But we're going to stick with Verilog. I believe the textbook goes through both, has a chapter on each. So we're just doing Verilog. And the main piece of the stuff we do in Verilog is called a module. So a module is kind of like a function in programming. So everybody here has done engineering or CSE 120, so you've probably done some Python, and you may have done C or something else on your own. So modules are kind of like functions. They basically describe something like this, right? They describe what's going on inside a box of a system diagram. And so when we write a function in programming, we have arguments, right, that you pass into the function, and we sometimes have a return value that comes back from the function. So our functions in programming languages have a notion of inputs and outputs. Or maybe, you run a program and a person types something at the keyboard, that's an input, and maybe the program prints something that's an output. So our Verilog modules will also have this notion of input and output, but here we're really talking about what are the things going into this box, what are the things coming out of this box. And we're going to use Verilog to write a description of what's going on in this box. How do these inputs get turned into these outputs? And so when we want to start a module, we'll usually do something like module, I don't know what we might call it, mod 1, parentheses, and we list the inputs. So, A, B, X. And we might say something like A and B are inputs. And we might say X is an output. So what we're listing here are basically the names that we're going to use inside our code to describe each of these things that's associated with an arrow. So we might do input WSE and output GWGSGE. Here's the cool part. Now we could say something like, X equals A and not B. And we use a special keyword here, assign X equals A and not B. And then we might say end module. Well, this set of code creates the following. It says, let's make an AND gate. Let's take an inverter. Let's have this AND gate take the A input and the inverter output, which comes from B, and let's take the output of the AND gate and send that to X. And this set of things that looks like code will correspond to this circuit. And this could be, an extremely complex equation with several variables, and the software will come up with a circuit that not only, achieves this behavior, but does it with a minimal amount of hardware. It will do all of the K-maps and all of that stuff for us and come up with this nice circuit. And this is as far as we're going to go in this course. We're going to basically use this Aldec tool to let us enter in Verilog to describe different modules, compile them to turn them into circuits internally, and then run simulations. And our simulation will say, okay, I want to take A and I want to toggle it every 20 nanoseconds, and I want to take B and I want to toggle it every 40 nanoseconds. And I want the software to tell me what X looks like. And it will simulate the behavior of this circuit and show us the resulting value of X. And looking at these, we can then say, is our circuit doing the right thing? Right? Is our circuit always high exactly when A is high and B is low? Now, that's as far as we're going to go with this, but if we were doing this, as part of our job or something, we could continue beyond that point. And one thing you can do is you can take this description of your circuit and you can send it to a foundry, a chip manufacturer, along with, a few $1 million, and they will make a chip for you. And sometime later you get a package and it's got a bunch of chips inside that correspond to this circuit that you built. And pin 1 might be A, and pin 5 might be B, and pin 3 might be X. and you can hook up switches and LEDs and so on and so forth. That's a really expensive process, and it's really slow, and it's phenomenally expensive. To get one chip made from a Verilog description is going to run, you know, multi-millions of dollars, and it's going to take time. And if you mess up, if you really wanted, you know, this to be a C instead of an A, you throw your chips away, you ask your boss for a few more $1 million, and you try again. So we don't usually do that. We use instead things called FPGAs. So an FPGA is a field programmable gate array. This is like the PALs and PALs and PROMs we talked about a few weeks ago. It's a piece of hardware that you can program. You can hook it up to your laptop, and after you've come up with a design, you can say, program this chip. And you can send information into it, and it will basically customize the guts of the chip to look like this. And FPGAs are really the way that engineers go from a desire for a circuit to something like a Verilog module, to a simulation, to a verified design, to an actual piece of hardware. And more systems that you find that have custom hardware inside, that hardware is really built on top of FPGAs. So Cisco was kind of an industry changer when they started doing their routers decades ago. They used FPGAs to build the custom chips. And routers, you know, they have to work extremely fast because they're dealing with network speeds. It's hard to do that with a CPU from the 80s. So they were doing custom hardware, but they did it on top of FPGAs. So this is the same process we're going through to explore Verilog and circuit design using a hardware definition language. All right, so I would say download this this Verilog intro from Canvas, and at least keep this PDF handy, because we'll be going through it and putting in some of this code into Verilog and so on and so forth. Definitely try to download the Aldec software and get that running on your end. I'll do the same on mine and get that running with a monitor I can share during Zoom. And then we'll start going through some examples of this and digging more into the concepts of hardware languages on Wednesday. Office hours tomorrow morning as usual. If I don't see you there, I'll see you next time. All right, thank you. You're welcome. Yeah, go for it.